Once again, yes, recording has started. Now you can start, Dietmar. Thank you.
Yeah, so welcome to my presentation of SerenaOS, which is a hopefully modern operating system for the Amiga. Admit what? Okay. So what's the agenda? First of all, let's clarify the question what the thing is and what exists so far. Why? It's a very good question. Why I even bothered with this. Then I will talk a bit about the kernel and things like dispatch queues, file system console. Then we will move on to the user space, so the Serena shell. I will talk a bit about how to build it, the build tools that come with the project as it is on GitHub. And last but not least, we will taunt the demo gods a bit today and see how they feel, whether it's going to crash or not. So what is this Serena OS about? It is a POSIX-inspired operating system, but that said, the goal is not to make it 100% compatible with POSIX. The goal is not to create a POSIX clone. It's inspiration, a starting point, and then there will be additional ideas and different ideas where it will go in a different direction compared to POSIX. SerenaOS is a pervasive preemptive multitasking system, so multitasking is always on. And this is very different from how the Unix system used to work back in the day when the Amiga was the king of the hill, so to speak. Back then, in a Unix system, preemptive multitasking only happened in user space, but the moment the application called into the kernel, preemptive multitasking was effectively turned off. And context switching would only happen explicitly, but not implicitly anymore. In SerenaOS, it always happens, whether in user space or kernel. And another thing where SerenaOS is very different from your run-of-the-mill POSIX system is that there are actually no threads in SerenaOS. Instead, it's all built around dispatch queues. So you have processes just like in a standard POSIX system, but the process starts out with a dispatch queue, and then you create additional dispatch queues as needed. And the dispatch queue basically manages the threads, so to speak, for you. So they are called virtual processors in SerenaOS. And the dispatch queue will automatically acquire a virtual processor when needed and relinquish it when it's actually not needed anymore. And then we have processes which sit on top of the dispatch queues. They're organized in a tree, just like in POSIX. But another difference to POSIX is in POSIX, you create a process by first forking, and forking just creates a copy of the currently running process. So all the memory is copied. And then in this new process, you execute an exec, and this then starts the actual executable you want to run. In SerenaOS, it's a single step, a spawn step that creates the process and runs the executable. It's much more efficient compared to what POSIX does. Then there is a driver model, which is tree-based. So you have a root driver in the system, which basically matches the motherboard. And then for each bus in the system, like in the Amiga, you have a server bus, you have the game board bus, you have a floppy disk bus. There's a separate driver matching that bus, and each bus driver creates the drivers on that bus. So for every floppy disk we find, we create a separate driver instance, and the whole stuff is a tree. Then there's a file system. It's a very simple file system, not particularly big, and a disk cache. And then finally, there's a console that currently implements VT52 and VT100 functionality. So what exists today is really a build system for Windows and macOS. For Windows, everything is supported, so you can build a kernel, and there are tools like a tool to create a disk image file, so ADF file for Amiga emulator. But the disk image tool is currently not supported on macOS. The whole stuff should be pretty easy to port over to Linux. I just haven't spent time on doing it. This build system creates a kernel as a custom ROM image that you can then basically burn into an EEPROM and stick it into a real Amiga, or you can just load it into an Amiga emulator. Then there's the file system. Like I said, it's very simple, but it gets the job done at this point. There's the console with the text-based user interface. There's also a graphic driver API that supports like selecting the resolution and creating sprites and doing sprite stuff, so changing positions and stuff like that. There's a event driver that supports mouse and joystick and keyboard. And then you have a shell in user space, which is somewhat similar to the AmigaOS shell, but as we will see, it does some things quite differently. And then there's a disk image tool that allows you to create a disk image on your host system. So on Windows, you can create a disk image for an emulator, and you can copy files on there and create directories and stuff like that. So now the question is why? Basically, it boils down to I used to own an Amiga as a kid, and I played a lot of games. And I also wondered, how does the operating system work? How do I implement this? But the problem back then was I didn't have the knowledge to actually pull it off. And today I'm a professional software engineer, so today I have the knowledge. And then COVID hit, and with COVID, I was able to move my work to home and work from home. And that's far more efficient, so I don't spend hours anymore commuting, and those hours are now going into this operating system. And it is fun. I do also have to say there are days where it's not really that much fun because it's very bare bones. So I have an emulator, but if there's a bug, there isn't really a shiny user interface-based debugger. So you have to stick like print statements in there. And in some places, you cannot stick a print statement in there because the problem happens like right where we boot. So all you can do is just change the color of the screen. And this can be very time consuming to figure out where the problem is if you need to debug that way. Okay, so how does this look from a kernel perspective? So at the very bottom, you have a hardware abstraction layer. And this guy takes care of things like interrupts and like doing the very initial phase of booting, all this very low level stuff and like the basics of how to implement a lock and how to implement a semaphore. And on top of that, you got the virtual processor system on one side, which implements virtual processor, which is kind of like a very lightweight kind of thread, but a thread that's not tied to a specific application that can move between applications as needed. So if one application doesn't do anything, you just move this over to a different application. Then on the other hand, you have the driver system. The drivers implemented as objects. In contrast to POSIX and Linux and those guys, there are no block drivers and character drivers. Basically, there are different classes of drivers. And you have one class for disks, you have another class for like graphic drivers, another class for sound, and you then subclass this stuff and create a specific driver you need. On top of the driver, you got the disk cache, which just caches individual sectors of a disk. You got the file system stuff. The file system stuff is very flexible. So a file system by default does not assume it's going to work on top of a disk. It just defines a namespace. We'll say, here's a name, and this is backed by some kind of object. And that's the basic file system stuff. And then you have containerized file systems, and containerized file systems say, I sit on top of a container, and this container then sits on top of a disk cache, and you can get blocks from the cache and write blocks to a cache. And then back over on the other side, we got the dispatch queue sitting on top of the virtual processors, doing their thing. We will then see what exactly it does. Then you got processes. A process is basically a collection of dispatch queues. And at the very top, we got the system calls. So in SerenaOS, you really have a separation of user space and kernel space and system calls. So dispatch queues are a big difference in SerenaOS versus the other operating systems that existed back in the day. So they really replace traditional threads. There are no threads in the traditional sense. And the dispatch queue, you can really see it as a queue of work to do. And underneath, you got a set of virtual processors, and the dispatch queue basically takes walk and dispatches it to a virtual processor. And the dispatching can either be immediate, where say, I want this to run right now, as quickly as I can, or you can say, run it at this time or after that time, like run it at 12 p.m. And then it can say, okay, run it at this time, and then every couple seconds. And the way this looks is basically you got either serial queue, where you have like walk items, like walk item A and B and C and D and D, and they just stick it in the queue. And then you have one virtual processor that just grabs the next item from the queue and executes it. And the dispatch queue grabs the virtual processor from the virtual processor cache. So if the queue just sits there for like 5 seconds, doesn't do anything, then the kernel will actually take the virtual processor away from the queue. And this virtual processor can then be used in a different process for a different dispatch queue. And another option is that you have a concurrent queue where more than one walk item can execute at any given time. So here we have a queue with 4 virtual processors, and it can then execute 4 guys at the same time. This is not that super interesting on a single CPU system like the original Amiga was, but on a multiprocessor system, it will be more interesting. And so in that sense, SerenaOS right now targets the Amiga, but the whole thing is designed that in the future we can target other hardware like Atari TT or maybe actual multi-core systems in the future. But that's further down the line. Then you got a simple file system. Right now it just supports the floppy disk. I don't have a hard disk driver at this point. It's one of the things that will hopefully happen later this year. Currently, the file size is limited to like 128K, also something that will be extended in the future. It supports directory hierarchies and user group-based security system like you find on Linux, for example. The file system structure is organized in this way that the kernel actually takes a lot care of things that file systems need to do. And the file system class itself only handles the very basics, the very low-level parts of the file system specific stuff. So in the kernel, you have a file manager, and this guy actually implements the overall semantics of, this is how I create a file. Like I get a path, and I need to map the path to a location in the file system at the directory. And we need to do security checks. And I need to check whether the file might already exist. So the file manager takes care of that. The file system doesn't care about that at all. It just does the file system specific part. And then you have a file hierarchy object, which really does the mapping of path to a file or directory. And that way it makes it much easier to implement the file system. And it also opens the path towards a total virtualization in the future, where you can say, I start an application, and this application sees the whole file system as you boot it, the operating system. And this application can now create a child process, and this child process gets a completely different file hierarchy, where maybe instead of the floppy disk, it sees a different file system as the root, like a RAM disk, and where as a certain other file system might be mounted at a certain place. So it can get a completely, totally different file hierarchy that way. And then finally, there's a console in there, which implements VT52 with some AtariSD extension. So the AtariSD defines some extension for more color handling. And then there's VT100 compatibility in there. The resolution is currently hard-coded to 640 by 200 at boot time, but the console itself supports 640 by 400. But right now you have to recompile the kernel to switch the resolution, so there's no command line tool to do it. Input-wise, you can either do blocking or non-blocking input. And currently the console still lives in the kernel, but I want to move it into user space that it basically runs as a daemon or background service there. but we're not quite there yet. Then in user space, we have a shell. The syntax is similar to the AmigaOS shell, but one huge difference to AmigaOS and basically POSIX shells is that in Serena shell, everything is treated as an expression. I will show later in the live demo what this means in concrete terms. One other big difference is that you have to explicitly declare variables. So variables are not kind of falling from the sky as they're doing in typical shells. You have to declare them. And that avoids problems like you misspell a variable name, and now you suddenly get totally different behavior in your shell script. The shell also has a number of built-in commands like list, delete, rename. Load is a command to load like the content of a file, and then you can assign it to a variable, and save, you can save the content of a variable to a file. How do you build this thing? In principle, all you need to do is just install Visual Studio Code, and you install the VBCC compiler toolchain from this web page, and you check out the project from GitHub, and then the first step is to compile or run the make file to compile the build tools that are part of the project. And then just open Visual Studio Code. You hit Control-B and select Build All from the menu. And there's it. And then it should work. On Windows, it works that way. On macOS, it works mostly that way. But when I then try to run the kernel in the macOS simulator, you might get a crash, because the VBCC compiler, depending on the version for macOS, might miscompile the code actually. Build tool-wise, so there are certain tools that come with the project. There's a make ROM tool to actually package the kernel into a ROM. And there's a lib tool, which is kind of like an ER tool, but for Windows. So it takes the binary that VBCC generates and then packages it up into executables that this actually works, because the ER that comes with the Microsoft tools doesn't work with the VBCC output. Then there's a key map tool to generate a key map from an ASCII description, so that the system knows, okay, when I press this key on the keyboard, we should generate this character or this escape sequence. And all of these tools are supported on Windows and macOS. And then there's the disk image tool, which you can use to create an EDF disk image on Windows or macOS and format it with Serena OS. You can push a file on there. You can pull files off there. You can create directories, list directories, and you can get individual disk blocks and replace disk blocks and stuff like that. But right now, this is only for Windows. It shouldn't be a big deal to port it to macOS. Just haven't had time to do this. Now, let's see what the demo gods are thinking today. If I can actually get my... okay. Apparently, there we go. So basically, you can use the emulator like WinUE to run this. There's also macOS version, Linux version. And all you do is that you set up a system that has a 68030 in there. It doesn't really matter whether it's a E4000 motherboard, as long as it has a 68030 in there. And then you load this, and this is my not very professional attempt to create a logo for the system. And now the system is logging you in. And basically it logs you in as the administrator, and you have your own home directory. When you do a list, you get something that's similar to what you would get in POSIX systems. So you get the permissions. The first three are your permissions as the owner of the file, like R means you can read it, W means you can write it, the X means you can execute it, so it's executable. Then the next three are the permissions of the group, when you belong to a group. And then the last 3 are the permissions of everyone else. And then I got the link count. So the file system does, in principle, support hard links, but currently there's no user space command because the kernel doesn't check for loops at this point. And then the user identity, 1000 in this case, group identity, size of the file, date when was created, and the name. And then let's see, you can run a shell script by using the shell command. And here it is executed immediately because it just so happened that the hello world shell script is on the same track as the directory. And because of that, it got pulled into the disk cache. And you can run like other things like prime numbers or like the loop program. So this runs like 10 iterations of a loop and then prints out the 42. And here you can see how the shell syntax looks. So the echo is just like in any other shell. It prints out the text. \m means terminate the line with a new line. And then here the var $i equals 0. This is a declaration of a variable. So var means that this variable can be modified. There's also a let, where it means that the variable is a constant. It cannot be modified once created. Right now, variable names have to be prefixed with a $, always. This will likely change in the future, that you don't need the $, anymore. And then I can assign an initial value to it. And so we have I, the loop iteration variable, and then we have sum that we set to 32 in the beginning. And then we have the while and the condition of the while. So basically run it 10 times. Then the body of the loop is in braces. And here inside the loop, you might notice there's the $i at the end, which is kind of weird. And then you see the sum equals sum plus, which also seems kind of weird. And this is basically the expression thing. Everything is expression, including flow control. So the while does its thing. And when it's done, the value of the last expression is returned. So in this case, the last expression is I. So when the while loop runs, it increments the I up to the 10. And this is then the result of the while, and we add it to the sum, and that's why we get the 42. What else can you do? Yeah, you do have a snake game, which is like the most important thing. That's really why I implemented the operating system, so that I can play this and always fail it, because why not? You also have like a history in the shell. And one day I will actually be able to hit it. So you have the snake where it eats the stars and gets bigger, and when you hit the wall, then it quits. What else can you do? You can do things like write some text to the disk, and again, this basically happens instantaneously thanks to the disk cache. You can output this again, or you can say, hey, I want to assign this to a variable, and then you can output the variable. And if you want to work with an expression, then you can just stick it in a parenthesis, and then it will evaluate the expression and print this. And this is basically it. Any questions?
Many thanks, Dietmar. Really nice presentation. I had also a few questions, but you kept answering them while you were progressing with the presentation. I was just wondering about this file size limit. Currently, you have 128 kilobyte file size limit. Is that not blocking you for development or something like that when you have like big chunks of files? Or?
So basically, right now it's good enough, because currently the only persistent storage supported is the floppy disk and a RAM disk, but okay. Basically, where I want to take Serena FS is that for the representation of directories and the file structure, so the mapping of the file to actual disk blocks, that I'm going to use B trees going forward. But I didn't want to implement this right now because my debugging capabilities are very limited. So I have to do everything in like tiny little steps. And so right now I'm just using this same block mapping structure that Unix 7 used to use back in the early 1970s, where I just have a tree of blocks and that is it. So I didn't want to spend too much time on this because the next step is implement B trees and then the limit will go away and the vector lookups will be much faster compared to now. Because right now it's just a simple list of stuff.
Okay. Actually, talking about debugging, there was a question from Alper as well. He was saying, why not use the serial logging feature of WinUAE to debug? So you are using WinUAE actually. So.
Yeah, it's, I guess I'm just a bit too lazy. So I started out with WinUAE and I actually rarely use the debugger that's built into this. It does have a debugger built in where I can show like the meshing code and look at memory, but I actually rarely use this too. It's really just printf and changing the background color. I guess I just got used to doing things that way, or maybe masochism knows.
Okay. I was impressed by the shell, the Serena shell. It looks quite advanced. Is it documented as well there on GitHub? Or I did not have a look
Yeah,
yet.
okay. It is documented on GitHub. So the basic direction in which it will move is there. There are some things that will change. Like right now that every variable always has to be prefixed with $. I think I will change it so that in the future, when I declare it with the var, like here, that I don't need the $, and that you can just use the $, as a shorthand for doing the declaration. So that it's on one side more compatible to what people are used to from POSIX. On the other hand, that it don't have the $, all the time there. It's currently a limitation in the parser. And I also want to add things like syntax highlighting and stuff like that. So what the shell does internally, it is actually based on an actual real grammar. And so there's a real parser that generates a syntax tree internally, and then it interprets it. And because I have a syntax tree, I will be able to do things like color highlighting in the future.
Nice. Okay. One last question from my side. So when you launch, you selected the 68,000 architecture. Is it also supporting other architecture like PPC or something? Yeah.
Not at this time. So it's one thing I want to do in the future to support like Atari TT would be nice, and PPC, and also modern hardware at one point, like modern x86 multi-core. The kernel internally is implemented under the assumption there would be actual multi-core CPUs. So everything does proper logging and is designed with multi-core in mind, that we can actually take advantage of it if it's there. It's just right now I do it for the Amiga because as a kid, I wanted to do it. So I have to follow through finally. And in the future, it will grow bigger.
Yeah, good, super nice. I don't know if there are other questions. So we have also an OS specialist who has joined the call in the meantime. Sven, welcome. I see another question here. Any plans to implement a graphical user interface?
At one point, I want to do a graphical user interface. So basically, user interface-wise, the next step will be to move the console out from the kernel into user space, because in my mind, it doesn't belong in the kernel. It's a convenient way to get off the ground, but the UI has no place in the kernel. And even if it's text, it's still UI. So that's the next step. And then I want to do a Windows server and build an actual UI, but very likely not with the C language, because C is just so extremely limited if I want to do any OO UI related stuff. So this will either be C++ or maybe my own language. I do have some theories, ideas for my own language, which would be similar along the lines of Kotlin or Swift further down the line in the future. In that sense, if anyone has interest in participating in this, I would very welcome any kind of help, because right now it's just me and it's a huge project. And there are a lot of things where people could just smooth into it. Like there are certain bugs that require more investigation. Like currently, when you write to the disk, sometimes actually the track gets messed up, where a certain block gets replaced with the super block of the file system. And I don't really know why, actually. It doesn't look like a dangling pointer because it's exactly the super block. And if someone wants to look into this and just do more testing to kind of get a better idea of what's going on, that would be extremely helpful.
Okay. So I think the call is was launched. Let's see. You welcome anyone, even if they program only in C?
Yeah.
Okay.
So,
Any other
and
questions, serious questions from the attendees? Don't hesitate to unmute and ask any question. If not, then I would say many, many thanks, Dietmar. Really nice presentation. I will stop the recording now.